So right now, let's imagine that we want to solve the, let it be again. Well, let it be simply the diffusion equation. Diffusion equation in 2D. And we want to solve it in the square domain. So what we would do, we find differences. We introduce the domain subdivision. And we need to introduce two indices, y, I and j. We've got the ascending order, and we need to, first of all, what we need to do is, remember we want to have some solution vector. Solution vector that will be storing all u values. So what was the first, okay, maybe not ui, let's say uk. So the first thing that we need to agree on is we need to introduce some numbering. Then there are at least two conventions. We can either use only these values, the internal nodes, and depict them as unknowns. But the other convention would be to also use all the values lying on the boundary. Right. Now, if we are using only the internal nodes, then what's the advantage?
It's easier to enumerate the nodes.
It's easier to enumerate them. There are fewer unknowns. However, you need to take care of the implementation of the boundary conditions properly. It's easy. It's extremely easy if the boundary condition is simply 0. Because what? Because discretizing the equation, if you've got just in one direction, you would have ui minus 1 minus 2, ui plus 1. And let's assume that we are, for instance, writing the equation for that node. What does it mean? That obviously ui plus 1 does not exist. So to say, you would move it to the right-hand side from the matrix. Let's say minus. But it doesn't exist. If you do not replace it by anything, it means that you've got 0 in your right-hand side vector. So to say, using internal nodes and not using the external, the boundary nodes at all, means that you have automatically implemented the 0 Dirichlet boundary condition, right? So you need to take care of that if you want to have any different boundary condition on the boundary. Either you need to take care of that, introducing proper Dirichlet values, or you might need to replace it by something different if you want to implement the flux boundary condition, so the Neumann boundary condition. We can use this convention with introducing these red boundary nodes into our system. That's okay. Then we would come up with the same what we had for our 1D case, that you need to use some ones to implement the boundary conditions. One more question is, okay, I will be writing the equation. Let's say I will start with that node. And what's my stencil? My stencil for the 2D case is obviously taking this one, this one, this one, but also this one and this one to discretize the space derivative in that other direction. That's okay. Then we've got this as unknown, this one as well. So we are perfectly fine with writing such an equation. This one, for this one and for that one, we'll write yet another equation that implements the boundary condition. That's also fine. What happens with the numbering? It's pretty nice to have the numbering running in some reasonable order. So you'd probably want to add this node, this node, this node, and this node to the system as well. But you see, they obviously do not contribute to any of the equations. Like they are completely artificially introduced just to make a nice structure and nothing else. Very, very often in finite difference method, you start with the, you're introducing the following numbering. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. And I want you to, well, guess right now what the matrix structure would be for such a system. Can you already imagine if we use such a numbering? And then probably, if I'm not mistaken, this one would be 49. And we're trying to assemble the global matrix. What's the structure of that?
It would still be multi-diagonal, but with a wider spread, I would say.
Mm-hmm. That's true. Let's see, we've got 1, 2, 3, 4, 5 internal lines, and again 2 boundary lines. So first of all, let's draw 7 blocks. And again, as previously in the 1D case with the boundary condition, we knew that we needed to treat the first node differently. So in this case, we know that the whole line will be a bit different than the first internal equation. So let's start with, so to say, with everything that represents the second block. And here you can imagine we are starting with such a structure. And what's D? D, in our case, is nothing else as the one-dimensional D needs to implement the second derivative in the x direction. So generally ui minus 1 minus 2 ui plus ui plus 1. So what's D? D is minus 2, 1, 1 minus 2, 1. And let's write it minus 2, 1, 1 minus 2, 1. It's already 4, 1 minus 2, 1, 1 minus 2, 1, and 1 minus 2. 4, 6, 7. Okay? So that's D, and D goes everywhere here. Can you imagine that? Like if we are taking If we're taking the second row, this means that we're on that line, and then it means that writing the the first equation is, so to say, I can only refer to the neighboring node on the right-hand side, but I've got nothing on the left. That one is already, everything is fine. -2, 1, 1, and all these three nodes are associated, so that's that. And that discretizes, that already discretizes the second derivative with respect to the x variable. But for that node, we need to add something more. We need to discretize the derivative of u with respect to the y variable. Okay, so we need to move back by, so to say, in our numbering, we need to move back to here, so by 7. So this means that we need to introduce one additional matrix, the identity matrix, which is nothing else like 1, 1, 1, 1, 1, 1, 1. Okay? And we need to go one line higher. So again, we have the identity matrix here. Now, one small modification, implementing okay, that's j, ui, j, j. Then we need to implement discretize the second derivative with respect to y, again by u, I, j minus 1 minus 2 ui j plus u I j plus 1 equals 0. So like minus 2 uj minus 2 uij means that this one is not really minus 2, but here everywhere we've got minus 4. Okay, so and we need to know what's here. It's d I d I. Is it clear right now? So right now our matrix still has got this, well, diagonal structure, but right now we would say it's block diagonal. So you've got matrices that build the diagonals. You've got the D matrix, which is itself 3 diagonal. Each of the identity matrices is just one, has got just one element on the diagonal, and well, you got the block diagonal structure of the matrix. Questions? Because this one already concludes everything that I had to say about the finite difference method. So in a while we'll make a short break and we will be moving to the finite volume method.
Maybe one strange question. Is it possible to construct finite difference on unstructured mesh grid? Possible, maybe yes, but is it viable?
No. Like I think if you try hard, it's possible. You need to develop some stances that can work. You know, even if you've got something. Well, if you've got something like that, you can probably still come up with some discretization of such a stencil, probably using the gradients in this at this position and the directions of these lines, where you probably could. No, but it's not. It's not something that is done. And actually, because of that, the finite difference method is something that is commonly used for simple geometries. Like if you've got rectangles, squares, etc., it probably makes sense to use the finite difference method because it's extremely simple. You can implement it quickly, but I haven't seen any codes that would work in complex geometries with the finite difference method. Although it's possible.
Yeah, it's kind of use some chimeras to interpolate between meshes and.
Like I've seen some concepts, but I would rather call it concepts where you've got strand geometry and you are building finite differences.
Kind of immersed boundary.
So to say, and then what you're doing is if you need to implement the boundary condition here, so what you're doing is you're recalculating what's the distance here. So you haven't got a constant step size. You've got something smaller, and you can derive the discretization formulas for such stencils, and this can be done. But yeah, but there are better methods to discretize complex geometries.